Good day, everybody. Once again, we're back together, and this time we are looking at the Gauteng June exam. I know some of you recently wrote those exams, so if you have not subscribed, please just make sure you're part of the family. Right, let's quickly have a look at what this question paper entails. And by the way, we've got our camp that's coming up between the 1st and the 5th of June. So if you want to improve your maths or science results, make sure that you join us for that. All right, so let's join in so that we can see what this paper has. All right, so we start with the multiple choice section. Right, so they say two forces F1 and F2 are applied on a box lying on a frictionless surface, right, as shown below. The magnitude of F1 is greater than the magnitude of F2. All right, so now they say the box will. So note in this case, it will definitely accelerate because there is a net force, right? So it will accelerate in the direction of the net force, which would be to the direction of F1, since we are told that F1 is greater than F2. So it will accelerate to the right. So the correct answer there should be B. Right, and they say to us we've got a 5 kilogram iron shot put and a 10 kilogram aluminium shot put with the same diameter. They fall freely from the shelf that is 12 meters above, right, from the ground. So they say ignore the effects of air friction. Right, now they say when the shot puts are 3 meters above the ground. So note they come from the same height and they are going down and they are now 3 meters above the ground. They have the same. Okay, now I want you to note that as they go down, because they are free falling, their velocities should be the same. However, remember that momentum is a function of mass and velocity, and note that their masses are not the same, right? And then secondly, acceleration, definitely they would be accelerating due to gravity, and so as a result the acceleration is the same. And you'll note that both potential energy and kinetic energy are functions of mass, so there is no way that those would be the same as well. Right, and 1.3, they say two asteroids S and T having masses m and 2m respectively are on course for a collision. Right, now they say if the magnitude of the acceleration of asteroid S is A, so meaning if we look at asteroid A, F is equals to m times A, right? So that would be the acceleration, which is A, right? So they say then the magnitude of the acceleration of asteroid T is, now note, ladies and gents, that acceleration is inversely proportional to mass, meaning if we wanted to find acceleration, their net forces are the same. Remember, they're equal and opposite, right? So as a result, they exert the same amount of force on each other. The only thing that's different is now the mass, right? So the mass is 2m, so that means that it will be actually half the acceleration that we had before, right? So note in this case, it should be a half of A. Right, the next question. They say a sound source approaches a stationary observer at constant velocity, very important. Which one of the following describes the observed wavelength and frequency? Now note they said approaches, right? So meaning that the sound source is moving towards the stationary observer, right? So we know in this case that the observed wavelength, so remember when I'm approaching, the wavelength should be shorter, right? It will be less than, or rather, the observed wavelength should be shorter than the emitted, the wavelength of the source, right? So now let's see. They say the wavelength and frequency from the sound source as it approaches, right? So firstly, observed wavelength is definitely less than, right? So that would be less than, but let's look at the observed frequency. So remember that frequency and wavelength are inverses of each other, right? So the observed frequency should be greater than. So let's look at that combination. So that's less than and greater than. That should definitely be D. Okay, right. Now let's go on to the next one. They say we've got two objects, M1 and M2, at a distance R apart, right? Experience gravitational force F, right? So which means that if we were to express that, F is equals to G M1 M2 divided by R squared. Essentially, that's what they are telling us. They say the mass of M1 is now doubled and the distance is halved. So they want us to find out the gravitational force between M1 and M2 is now. Now note, we started with force F, but now what will be the magnitude of our new force, right? If we now double the mass of M1, so it will be 2M1 times M2, and they say to us we half the distance, right? So that means we've got a half of R, okay, squared. Now notice at the top we still have 2, so this will be 2G M1 M2. Remember that multiplication is commutative, so which means that we are essentially going to have the same, we can rearrange them, so I only put the 2 this side, it doesn't change anything, right? Now I want to get rid of the 1 over 4 at the denominator, so I'm going to multiply by the inverse, right? So 4 over 1, so what I do at the bottom I do at the top, that's 4 over 1. Okay, so what do I eventually have? That's 8G M1 M2 over R squared. So which means the force is 8 times what we had originally. So that would be 8F. Okay, so that's D. So the next question, they say an object is thrown vertically downwards towards the ground from the height h, right, with a velocity v. The object strikes the ground and bounces upwards. It is caught when it reaches its maximum height above after the bounce. Right, so firstly, we know that we are going to throw an object vertically downwards, right? Okay, so we know that the initial velocity cannot be 0, all right? And then we know that the object will strike the ground and it will bounce upwards, right? In this case, they say which one of the following graphs of velocity versus time best represents the motion of the object. Now, first of all, ladies and gents, we know that our initial velocity cannot be 0, okay? And so what happens? Our velocity starts from a certain height, and of course it's going to increase as we go down, okay? And of course it changes direction when it gets to the ground and bounces upwards. All right, now I want you guys to please note, if we took downwards as positive, right? So what's going to happen? It's going to start with a positive velocity, and of course it's going to increase, right? Until we get to the ground, okay? And on the ground, what happens? It changes velocity, right? And now look at that velocity. It becomes negative, and what begins to happen is that it decreases. So this looks like the correct graph, which is A. All right. Now, if I look at B, can you see those gradients are not the same? Remember that the gradient should be the same because it represents gravitational acceleration, right? So for those two graphs, we should have the same acceleration. Now, why can it not be C? Because C seems to suggest that our velocity was going up until the object stops, and then it changes direction. So this would have been an object that goes up, stops at maximum height, and then comes back down, right? And then only to change direction when it gets to the ground, and of course it goes up until maximum height. And that's definitely not what we're given. Okay, the same thing is true with D. We start at a velocity and it goes up until maximum height. So that is why the only possible answer could be A. All right. So let's go to the next question. They say a crate is pulled up a slope. Which of the following will do zero work on the object? Okay. So remember, in this case, we are pulling it up a slope. So there we go. Okay. Here's our object. We are pulling it up a slope. Okay. So which forces do zero work? It would be the normal force, right? Because it's at 90 degrees. But again, it would be the perpendicular component of gravity. So those two forces would do absolutely zero work in that case. So let's see. They said normal force, definitely B. I would tend to agree with that. Okay, and in this case, they didn't say the component of gravity, but they said gravitational force. And gravity does a certain amount of work there. Okay, because it has a parallel component as well. So that would be B. Now they say to us, we've got three identical spheres, X, Y, and Z, that are placed together in a triangular arrangement so that each sphere touches the other. The three spheres are then moved back to their original positions. Right, now please remember, once we cause spheres to touch, what we'll have, or what we will do, is that we now would cause charge to then flow, all right, from the one to the other. Now, because they are identical spheres, the charge, once you separate them, the charge on each one should be exactly the same. Right, so what we're going to do is take the charge on 1, charge on 2, charge on 3, right, and we're going to divide by the number of charges that we have, right? So we've got -5 plus 0 plus 2. That would give me -3, right? Okay, and so -3 divided by 3, that will give us -1 nanocoulombs, right? So that would be the net charge on each of the sphere after they are separated. All right, now let's go to the next one. They say a positively charged object has, okay, so we know once an object is positively charged, it means that it has got a shortage of electrons, or we can say it's got excess protons, positively charged particles, right? So they say it has fewer electrons than neutrons. No. Fewer protons. No. Fewer electrons than protons. That is absolutely true. Okay, right, so there's a deficiency of electrons there. Okay, and finally 1.10, they say the minimum resistance that can be acquired from the connection of two 4-ohm resistors is, now remember, if we place them in parallel, ladies and gents, that's when we can get the minimum resistance. And of course, if I've got 4 ohms and 4 ohms, right, it means that the resistance of the two resistors, right, will simply be 2 ohms. Now remember, all we can do is R parallel. That's product divided by the sum. So R1 times R2 divided by R1 plus R2, right? So that would be 4 times 4 rather, which is 16 divided by 4 plus 4, right? That's product over the sum. So that would definitely be 16 divided by 8, which would be 2 ohms. Okay, so just remember that whenever I've got resistors in parallel, right, and they are equal in resistance, then the effective resistance in parallel will be half one of them. So that means that our minimum resistance there should be 2 ohms. All right. So ladies and gents, that is how we come to the end of question 1. Let's go on to the next one. Right, let's go on to question 2. So they say we've got block M, which is 10 kilograms, that is connected to block big M, which is 10 kilograms, is connected to block M, small m, 2 kilograms with a rope T of negligible mass over a frictionless pulley. Both blocks are at rest. Okay, so that's very important because it tells us that our system is at equilibrium. So they tell us that the slope makes an angle of 30 degrees with the horizontal. Friction on the slope cannot be ignored. So meaning that there is definitely friction on the slope here. Right, so they say to us we must define normal force. Now remember that normal force, ladies and gents, is a force or a component of a force, right, of an object with a surface, right, that it is in contact with that is perpendicular to the surface. Okay, so please remember that definition. Now note the next question. They say draw a labeled free body diagram, right, of all forces acting on the 2 kilogram mass. Now notice for the 2 kilogram mass, we know that we are going to have the force of, or rather the tension. Okay, so we're going to have the tension of the string, right? So tension on string, right, as well as the gravitational force. Now notice, try as much as possible, ladies and gents, to make it visible which force is bigger than the other. Now, because our system is at equilibrium, it means that our tension there should be equal to the normal force. So this would be, in fact, let's just make it easier for ourselves. Let's say this is the weight, okay, of mass M. So that's the free body diagram. And note, as I did say to you in previous times, that the amount of forces that you have will be indicated by the Mach allocation, right? So that is how we're going to answer that question. They say calculate the friction, now in 2.3, the frictional force needed to keep the blocks at rest. Okay, now, which means now we are looking at the 10 kilogram block. So it is being pulled by the force, the tension there on the string. And we note, because we're dealing with the frictionless pulley, we know that the tension on the one side of the pulley should be equal to the tension on the other side of the pulley, right? So we can determine that tension, right? What is that tension? We can use the 2 kilogram mass and say, well, the tension, so this is for 2 kilograms. Okay, so we know that F net will be equal to 0 because the acceleration is 0 in that case. So which means tension minus the weight should equal to 0. So tension should be equal to that weight, which is 2 times 9.8, and that's 19.6 newtons, right? But now that's not what we are interested in. We want to find out, okay, what are the forces, or rather, the frictional force that acts on big M, right? So we said we've got the tension on the string, right? But what other forces do we have? We've got a gravitational force, in this case the parallel component of that gravitational force, so that's Fg parallel, that's pulling the mass downwards. But we also have the frictional force that's exerted on that guy. So that's friction there. Okay. So I know that I'm going to have, this is now for the 10 kg mass. Okay. I'm going to have the tension. Okay. We know the sum of the forces that are parallel, okay, will be equal to 0 as well. So that means I'm going to have tension, right? I'm taking force upwards as positive, or up the slope as positive, plus a negative friction, plus minus the the parallel component of gravity. And we know this would be equal to 0, okay? Right, I'm going to try and complete this on the other side. So this means that, now ladies and gents, it means that tension would therefore, because we're looking for gravity, right? So we know that our tension is 19.6, all right? That's minus Fg parallel. Now note, ladies and gents, Fg parallel, we know this is mass times gravity multiplied by the sine of the angle of elevation, right? So this is going to be 10 times 9.8 times the sine of 30 degrees, right? So if you don't know where that comes from, please go and watch my videos on Newton's laws, right? And we know this is now going to be equal to our our frictional force, right? If we took tension to the other, friction to the other side where we had a 0. So we know the value of friction. Okay, apologies. Let me just write this nicely. Okay, so we've got, we said tension, which was 19.6 minus Fg parallel. We said that's 10 times 9.8, the sine of 30. That's equal to the frictional force, right? When we take friction to the other side. So let's calculate that, ladies and gents. So we've got 19.6 minus 10 times 9.8, the sine of 30 degrees, right? And I get a frictional force value of 29.4. Actually, this is telling me that this guy is actually experiencing friction that's going up the slope. That's ironically, and it does make sense, because if you think about it, this mass is significantly bigger than the mass of the mass of the 2 kg mass. So the friction there, we got a value of 29.4. So this is going to be 29.4 newtons. Okay, right. So that tells me that actually, when I was calculating there, that friction actually should have been in the positive direction, right? Since I chose up the incline as positive. However, we're looking for the magnitude of the frictional force, right? So that must be 29.4 up the slope, right? Okay, right. Now let's go to the next question. Now they say to us the rope snaps, okay, above the mass M, causing the block M, big M, to slide down the slope, right, and block M to fall to the ground. The kinetic frictional force between the blocks and the slope is 25 newtons, right? So now they are telling us that we've got a frictional force value between the block and the slope, okay? That's 25 newtons, and they said to us we must ignore the mass of the rope. Now they say draw a free body diagram of all forces acting on big M. Now note, in this case, big M should slide down. So that means, remember, we no longer have the tension, okay? So we're going to have the parallel component of gravity, so Fg parallel, but we're also going to have the frictional force that's acting on big M, all right? In this case, please note, we also have the normal force, all right? So that's the normal force, as well as the perpendicular component of, so that's Fg perpendicular. If you didn't want to show those components, you can actually draw just the gravitational force there, all right? So these are the forces. So force of gravity, right, acting on this guy here, the frictional force, and please label in full, ladies and gents. So frictional force, okay, Please don't just write down the variables. When you write down the keys, make sure that you label in full. So you can say the weight, or you can say force of gravity. Okay, I don't have enough space to write all of that there, but I'm sure you understand. So this is normal force. All right, so let's go to the next question. They say to us, calculate the magnitude of the acceleration of mass m. So remember, we said horizontal, or rather parallel to the incline. We've got the force, right? The parallel component of gravity, as well as the frictional force. Those are the two forces. Remember that tension is no longer actively playing a role there, because the two masses are no longer connected to each other, right? So what we're going to say is F net is equal to MA, right? So that means that FG parallel, right, that parallel component of gravity, minus the frictional force is equal to MA. So that's going to be 10 times 9.8, the sine of 30, minus 25 newtons, right? Remember, that's the friction that we're given, is equal to 10A, right? So let's calculate that. So that's going to be 10 times 9.8, the sine of 30, right? That's minus 25. Okay, that gives us 24. So 24 is equal to 10A. We divide both sides by 10. And what we get there is an acceleration of 2.4 meters per second squared going down the slope, isn't it? Okay, so that would be the magnitude of our acceleration. Now they say to us, block M, small m, takes 0.5 seconds to reach the ground, right? And they want us to calculate the velocity, the final velocity of block M, right? So first of all, we've got the time, right? The initial velocity must have been 0, okay? And we know the acceleration. Remember, it is accelerating due to gravity. So what we're going to do there is we're going to say, well, VF, that's VI plus A delta T, right? We want the final velocity. We've got the initial, which is 0. Okay, our acceleration, going to assume that downwards is positive. So that will be 9.8. And the time that it took is 0.5. So in this case, that would be 9.8 times 0.5. That would be 4.9 meters per second. And that is down. Okay, so that is the final velocity of small m. Right, and then finally they say to us, how would the final velocity of m be affected if the mass was doubled, okay, and it is dropped from the same height? Okay, they say, right, only increase, decrease, or remain the same. Ladies and gents, please note it would remain exactly the same, right? So that's what we are going to say as our answer. But why is that? Right, now, if you note the calculation on final velocity, right, it was not dependent on mass, right? So we can say that equations of motion, okay, or the laws of kinematics, equations of motion are not dependent on mass, okay, dependent on the mass of the object, on the mass of the object. Okay. Alternatively, ladies and gents, you can mention that the object was moving vertically downwards and accelerating due to gravitational acceleration, right? So in that case, it means that the velocity should be the same, since it would not depend on the mass. Okay, right. So you can mention the fact that it was in free fall, right? And gravitational acceleration is not a function of the mass of the object. Ladies and gents, that's how we come to the end of question 2. Right, let's continue on to the next question. On to question 3, they say the Curiosity rover was dropped from 125 kilometers above the surface of Mars. The mass of the Curiosity rover is 899 kilograms, and the mass of Mars is 6.42 kilograms, 6.42 rather, times 10 exponent 23 kilograms. The radius of Mars is 53 rather, 0.25% that of the Earth. Now, ladies and gents, they want us first to state the, Newton's law of universal gravitation. And remember, how do we state that? We say that every object will attract every other object in the universe with a force that is directly proportional to the mass of the objects and inversely proportional to the square of their distance apart from their centers of mass. Okay, right, or you can say that, okay, the force of attraction between two bodies in the universe is directly proportional to the product of their masses and inversely proportional to the square of their distance apart from their centers. Right, that sounds like a mouthful. Right, they say calculate the weight of Curiosity on Earth. Right, so now if we wanted to find out the weight of Curiosity on Earth, all we're going to do is say weight is mass times gravitational acceleration. Right, we know the gravitational acceleration on Earth. Right, so we're going to just simply say it's going to be the mass, which is 899, times gravitational acceleration is 9.8. Okay, and if we calculate that, that's 899 times 9.8, and we get a value of 8,810.2. Okay, so that's 8810.2 newtons. Okay, so that would be the value of the weight of rover on Earth. Right, so that's 3.2. Now, let's go to the next question. They say calculate the gravitational acceleration on Mars. Now, ladies and gents, please remember, we were given the mass of Mars and we're given the percentage of the radius of Mars in relation to Earth, right? Okay, so, and remember, the radius of the Earth is always given. Please remember the radius of the Earth is 6.38 times 10 to the exponent 6. Okay, now, which means that the radius on Mars would be 53.25 over 100. So please remember that's a percentage, right? Multiplied by that value 6.38 times 10 exponent 26. So which means the radius there, let's try and find that radius. So that's that's 0.5325. Okay, times 6.38. In fact, you know what? Let's leave it exactly like that. So if I wanted gravitational acceleration, right, G is equal to the mass of Mars, right, divided by the radius of Mars. Remember, we square that. Okay, so the universal gravitational constant, remember, this is going to be 6.67 times 10 minus 11, right? We know the mass of Mars, that's 6.42 times 10 exponent 23. That's divided by, okay, so we said this is going to be 0.5325, okay, times 6.38 times 10 exponent 6. Remember, this is, remember that is squared, okay? So I'm going to use my calculator there. So that's 6.67 exponent minus 11, Okay, that's multiplied by 6.42 exponent 23. Okay, and this is divided by 0.5325, okay, multiplied by 6.38 exponent 6, and remember we square that value. Okay, so I get a value there, 3.71. So the gravitational acceleration on Mars would be 3.71, right, meters per second squared. All right, so there we go. All right, now let's go to the next question. They say to us, would the mass of Curiosity be different on Mars than on Earth? Choose yes or no. Of course not. The mass remains the same, isn't it? Okay, so they said, would the mass of the Curiosity be different on Mars? No, it would not be different, right? It would be exactly the same. Now, they want us to give a reason for that. Remember that mass is a measure of the amount of a body's inertia, right? So mass remains the same. Or you can say the mass of an object is the amount of matter, right, that you have on that object. So it would remain exactly the same regardless of where it is. Okay, right. So in that case, you can please just put that explanation there. But otherwise, that is how we come to the end of this question. Right, let's go on to the next one. So we move on to question 4. They say a learner standing at the bottom of a building throws a ball A vertically upwards at a speed of 11 meters per second. So I might as well just put in that information, right? So that's 11 meters per second. Okay, and they say, and the ball reaches a maximum height T. They say after 0.72 seconds, that's very important, right? They say another learner standing on the roof of the building throws ball B upwards. Okay, so ball B is also thrown vertically upwards. The two balls reach point T at the same time as shown in the diagram below. Right, so the first thing that they ask us is, what is the difference between free fall and projectile motion? Well, it's actually the same thing, right? This is motion of an object under the influence of gravitational force only. If you wanted to, you could say that free fall is the motion of an object under the influence of gravitational only. However, projectile motion, it's an object that is given in an initial velocity and moves under the influence of gravitational force only. But really, in truth, it is essentially the same thing. Right, so the first question, calculate the time taken by ball A to reach the maximum height at T. Now note, ladies and gents, from the ground to get to T, we know that the velocity at T should be equal to 0. The initial velocity was 11 meters per second. Okay, let me just fill that in very well, right? And we know that it moves under gravitational acceleration, right? So for 4.2.1, we're going to use an equation of motion, okay? And in this case, note we are looking for time. We've got initial, final velocity, and acceleration. So we can use the first equation. Vf is Vi plus A or G delta T. Our final velocity is 0. Oh, by the way, it's important when you're going to answer questions on vertical projectile motion, please choose a direction as positive. I'm going to choose upwards as positive, right? And it doesn't matter if you chose downwards as positive, not a problem. The only thing you need to remember is that, remember now that I've chosen up as positive, it means gravitational acceleration would be negative 9.8, because gravitational acceleration always acts downwards, towards the center of the earth, right? So I'm going to say our initial velocity is positive 11 plus negative 9.8. Remember, that's gravitational acceleration, and we're looking for time. So I'll take this to the other side. So I've got negative 11, which is equal to negative 9.8 delta t. And now we can divide by negative 9.8. And this is again a nice way to actually check if there are no mistakes, right? If you ever get time, as a negative, then it tells you that something is amiss. So that's 11 divided by 9.8. Remember, in this case, the negative divided by a negative, right, would give us a positive. So that's 1.12 seconds. Okay, so the time that ball A takes to get to the maximum height is 1.12 seconds. Right, now let's go to the next question. They say to us, calculate the initial velocity of ball B. Right, now I want you to note, ladies and gents, that ball B was thrown 0.72 seconds after ball A. Now that means that the total time of flight for ball B would be the time. Remember, they get to this point simultaneously, right? But in this case, what would have been the time that ball B spent on the air, right, in flight? So it would be the 1.12 seconds minus the 0.72. So you'd say 1.12 minus 0.72. So which means that ball B was in flight for 0.4 seconds, right? And now we're looking for the initial velocity. We know its final velocity at this stage will be 0, okay? So again, the very same equation. So for 4.2.1, for 4.2.2 rather, so I know that I'm going to say VF. Okay, so again, that's VF is VI plus G delta T. Our final velocity is 0. We are looking for initial velocity. Gravitational acceleration is negative, right? But now we know the time that it took. We said that's 0.4 seconds. Okay, so our initial velocity, right? So we're going to take 9.8 multiplied by 0.4. But remember, it's going to be negative on the right-hand side. When we take it to the other side, it becomes positive. It tells us that we're throwing this object upwards. So we get an initial velocity for B of 3.92 meters per second. Right, now they said the initial velocity, which means we must also specify direction. So this must be upwards. Okay, right, so that's our initial velocity for B. Right, so finally they said calculate the height of the building. So what I'm going to do there is that remember all right, let's talk about the displacement for ball A. If I took the displacement for ball A till maximum height, and I take the displacement for ball B, right, till maximum height, and I subtract them from each other, so which means this displacement here minus that displacement there would actually give me the displacement, or rather the height of the building. So let's do that. Let's find out the displacement for ball A. Okay, so for 4.2.3, I'm going to find And let's see. So we've got the initial velocity for pole A. Actually, yeah, we can. So we can say delta y. That's vi delta t plus 1 over 2 times a delta t squared. Okay, and nothing wrong if you decided to use delta y vi plus vf divided by 2 delta t, right? So let's find that displacement. Our initial velocity is 11 meters per second. The time of flight, we found that to be 1.12 plus a half times negative 9.8 times 1.12 squared. Okay, so let's find that total displacement there for A. So that's 1.12, right, minus 0.5, so I'm just multiplying by negative there, times 9.8 times 1.12 squared. Okay, so let's do that. So we find our displacement to be 6.17 meters. Okay, so that is the height for pole A. But now we find the height for pole B. Okay, so we're going to use exactly the same equation. So I'm going to say that's delta y vi delta t plus 1 over 2a delta t squared. So the displacement there would be, so if you remember, for pole B, we started at 3.92. But the time of flight for pole B was 0.4. That's negative 9.8 times 0.4 squared. Right, so now again, I'm going to do the same thing. So that's 3.92 times 0.4, okay, minus 0.5 times 9.8 times 0.4 squared. Okay, I hope that you are checking against your own calculations there. So delta y for B, so this is for A, this is for B, right? So B was displaced 0.78 meters, right? And in this case, now I want you guys to note, so the height of the building would be that 6.17 minus 0.78, and so let's find that height. So that's 6.17 minus 0.78, and I get a height of 5.39 meters. Okay, so please just check there if you do get to the same value. All right, and that is how I would calculate that. Okay, so let's go to the next question. They say to us, the following position time graph is given for the motion of the two balls, right, A and B, as described above. They say study the graphs and answer the questions below. Right, so definitely that is the displacement for A, right? That is on the first graph, and the displacement for B. Right, now they say to us, write down the value and unit, right, for X. Now, X would be the maximum height for A. We found that to be 6.17. So X would be 6.17 meters, right? Remember they said they wanted the unit as well, okay? And Y, so Y would be the height of the building. Remember, this is where we started throwing B from, okay? And we found that to be 5.39. That's also in meters. And they said Z. So Z would be time. Okay, so this is the time difference between when A was projected and B was projected, right? So if you remember, we said that time was actually 0.72. So that's the time delay at 0.72 seconds. Okay, and finally W, that's the total time of flight for ball A. In fact, not the total time of flight rather, but the total time until maximum height. That's 1.12. So that's 1.12 seconds. All right, and that is essentially how the cookie crumbles on this question. I hope that you got that. That's out of 19 marks. All right, and I hope if you understood this or you understand this section well, that's an easy 19 marks to obtain. All right, ladies and gents, let's go on to the next question. On to question 5. They say a wrecking ball is used to demolish an old building by smashing into it. The wrecking ball has a mass of 950 kilograms and is suspended in the air with a second rope. That's 3.5 meters above the ground. Okay, so I'm trying to just understand that picture. So there's our wrecking ball there, and it is 3.5 meters above the ground. They say the ball is then released. So note there, that means that its initial velocity is 0. To smash into the building, right, at the lowest or rather at the lowest point of swing, the ball is at a height of 1 meters, right, above the ground. Ignore friction. Now, they say to us, state the law of conservation of mechanical energy. Remember, we say in an isolated system, mechanical energy is conserved, or you can say in an isolated system, mechanical energy before is equal to mechanical energy after. Okay, right, so please note that. All right, or you can say mechanical energy remains the same in an isolated system. So for 5.1.2, they say the ball swings and hits the building at height h. Calculate the speed at which the ball hits the building using only energy principles. Now note, ladies and gents, so we've got a swinging ball, or we've got a swinging pendulum over here, right? And I want you to note our reference point is at 1 meter, okay, above the ground. So there are essentially two ways in which we can do this. We can use the ground as our reference point, in which case, if we do that, we're going to say, right, so Emec, so remember, because there are no external forces, right, so which means mechanical energy at the top, right, which means where the initial point, okay, will be equal to mechanical energy just at the bottom, right? So Emec at the top would be equal to Emec at the bottom, right? Now remember, I said this is when I take the ground as reference, right? Now if I take the ground as reference, remember kinetic energy, you remember I said to you, you must highlight the fact that it's released. So it tells you kinetic energy at this point, at the top, is actually 0, right? So there's no kinetic energy. Why? Because the velocity is 0, right? Plus the potential energy at the top, okay? And this would be equal to kinetic energy. So the ball, when it gets to this point here, possesses kinetic energy, right? So that would be at the bottom plus the potential energy at the bottom. Right, note that it would still have potential energy if we are taking the ground as our 0 position. So now we said kinetic energy at the top is 0 plus, okay, mass times gravity times height at the top equal to half mv squared at the bottom, okay, plus mgh at the bottom. Sorry that I don't have enough space there. Right, so the mass of the pendulum bob, okay, is 950 times 9.8. The height relative to the ground is 3.5. Okay, and at the bottom, this is half times 950, right? At bottom, that's the velocity we are looking for, plus the potential energy at the bottom. So that's that mgh. So that's 950 times 9.8 times the height at the bottom relative to the ground is 1. Okay, so please keep that in mind. Right, so ladies and gents, I'm just going to do all of that on the calculator. So I'm going to say this is 950 times 9.8 multiplied by 3.5. Right, so I'm going to take this to the other side and minus 950 times 9.8, okay, times 1, okay, and we get a value there which is 23,275. Now I'm going to divide that by a half of 950, right? So divided by 0.5 times 950, and I get 49. So which means the velocity would actually be the square root of 49, which of course I know most of you know that the square root of 49 would be 7 meters per second. All right, there we go. So that's how I would calculate it using principles of energy, using the ground as our reference. However, I could have also, ladies and gents, used the bottommost point that the ball reaches, which is 1 meter, as my reference point. So I could have said, right, so again, Emac, okay, top equals to Emac. Okay, I keep writing this incorrectly at the bottom. Okay, now note, if I use that point there, when it arrives at the building as my reference, then it means firstly my EK at the top, again it's going to be 0, plus EP at the top, so that's top, equals to, now which means the potential energy at the top relative to that point is only 2.5 meters. So I'll take the height difference between those 2 points, which is 3.5 minus 1. That would be 2.5, right? And so this would be EK top, right, plus EK bottom, right? Now, so I said top there, so that's EK bottom. All right, so now this would be half mv squared. Now note, we said the kinetic energy at the top is 0, plus that's EP, that's mgh, so that's 950. Okay, so let me just try to write it nicely. So that's 950 times 9.8 times the height would be 2.5. 2.5. And now note, which means when I take that as my reference point, it means there's no potential energy at the bottom, right? Because I've taken, in this case, my reference from that point of 1 meters. So this would be half m 950 times v squared. Okay, apologies about the space there. Okay, so now what I'll do is you'll do exactly the same thing, So that's 950 times 9.8 times 2.5. Okay, and I'll divide that by a half of 950. Okay, again I get 49. So I'll take the square root of 49, and that gives us 7 meters per second. Right, and please do note that that is how we really get to that value there. Right, in this case, it's very important that you choose a reference point in terms of that calculation. All right, now let's go on to the next question. They say the ball hits the wall. It takes 0.1 seconds to stop, right? So remember, it got to the wall at that speed of 7 meters per second, and it stops within 0.1 seconds. And they say it then rebounds. Calculate the magnitude of the force with which the ball hits the wall. So we're going to use our impulse momentum equation. So F net times delta t is equal to the change in momentum. We're looking for the net force, right? The time that it took was 0.1 in collision with the ground, right? So this is going to be mass times the change in velocity. Note, ladies and gents, that the mass of the ball, we said this was 950, right? Now, change in velocity is final velocity minus initial. And what happened to the ball eventually? It stopped. So the final velocity is 0 minus the initial velocity was the 7 that we calculated. Okay, so final minus initial velocity. And so which means that the net force that the wall exerts on the ball rather is going to be 950. Okay, multiplied by -7, right? That's 0 minus 7. And that is divided by the time, which is 0.1. So we get -66,500. And please don't mind about that negative there. It's telling us that it was in the opposite direction, right? But we were interested in just the magnitude of it, so which means we are just interested in the fact that it's 66,500. Okay, so that's the force that the wall exerts on the ball, right? Now, or rather, that's the force that the ball hits the wall with. So in this case, so that was 5.1, 5.1.3. Okay, so for 5.1.4, they say to us, write down the force that the wall exerts on the ball. Now, really, this is a an application of Newton's third law, right? So if body A exerts a force on body B exerts an equal but opposite force on body A. So if the wall exerts, or if the ball exerts a force on the wall, then the wall exerts an equal but opposite force on the wall. So the magnitude of that force would be exactly the same. Now, they said name and state the law of physics. That's Newton's third law. Newton's third law. Okay, and note in this case, so that's Newton's third law, and we said if body A exerts a force on body B, then body B will exert an equal but opposite force on body A. Right. Now, they said state rather the law in physics that is used to arrive at this conclusion. So please, you'd have to state that in full words. Okay, right, and that is really how we get to that. Now let's go on to 5.2. So they say a grade 12 learner with a mass of 75 kilograms is on a skateboard with a mass of 2 kilograms. which is moving at a constant velocity of 2 meters per second. So let's note there that the boy is 75, the skateboard is 2 kilograms, and they are moving at 2 meters per second to the east, say over a frictionless surface. Very important. They say a ball of 500 grams, right, moving at a speed v meters per second west is thrown to the learner. Now they say the learner catches the ball, and the final kinetic energy after this collision is 146 joules. Now they say we must calculate the initial speed of the ball. So note, ladies and gents, even if we try to use the equations, or rather, principles of momentum, there's quite a number of variables that we do not know. We don't know the velocity of the, of the ball, right? But we also don't know the velocity of the, the velocity of the entire system. That is the boy or the learner, with the skateboard as well as the ball after they collide. But they did give us the kinetic energy, right, afterwards. So I can now say that the kinetic energy afterwards, now note, it's going to be the mass of the learner, okay, learner plus skateboard plus the ball squared, right? So that's going to be v squared. So that's going to be 146 rather. So that's going to be 146. That's half off. The mass of the learner, that's 75. The skateboard is 2. Plus the ball. Now note that the ball is 500 grams, right? So to convert it to kilograms, which we work with in physics, we always divide by 1,000. So that would be 500 divided by 1,000, which would give us 0.5. And that's going to be v squared. Okay, right. So let's do that. Let's calculate that velocity. Okay, so I'm going to say 146 divide by 0.5, which is that half, times, so that's 0.5 plus, so this is going to be 77.5, right? The sum of those masses. And I get a value there. Let's take the square root because we're looking for v. So v would be the square root of that answer there. I get 1.94 meters per second. So this is the velocity of the entire system, boy, skateboard, and the ball after collision, right? Because they were moving as one unit. So now we can use principles of momentum. Sum of the momentum of their momenta before equal to the sum of their momenti after. Okay, so this would be, now remember to choose direction. So I'm going to choose direction to the east as positive. Very important for us to choose a direction there. You'll see where it comes in. So initially, we had the boy or the learner and the skateboard moving together. Okay, and this is initial velocity. And then we had the ball moving on its own. So velocity of the ball initial. And thereafter, we had the learner, the skateboard, and the ball moving as one unit. That's final velocity there. Right, so now let's substitute. So we're going to have 75 plus 2, which is 77. their initial velocity, remember, it was 2 meters per second. So that's 77 times positive 2 because they were moving eastwards. The mass of the ball, 0.5. Velocity of the ball initial, that's what we're looking for. And this would be now 77.5 because we're looking at the joint mass. But they were all moving at 1.94. And I'd assume that they were moving to the east in this case because, I mean, the ball is relatively small in comparison to the learner as well as the skateboard. So it would be 1.94. Right, so now let's try and calculate, ladies and gents. So that would be 77 times 2 minus, if I take that to the other side, okay, or in fact, let me take the 77 times 2 to the other side. So I'm going to have 77.5 times 1.94 minus 77 times 2. Okay, I get negative 3.65. So 0.5 VBI would be negative 3.65. So I'm going to divide both sides by 0.5. So the initial velocity, okay, so we've got divide that by 0.5. I get negative 7.3 meters per second. Now we get a velocity that is negative, and we actually expected that because the ball was moving at a, in the opposite direction. So which means that the velocity of the ball initially was 7.3 meters per second, right? In which direction? To the west. Okay, right. So that is really how we get to the end of that question. I hope that you really understood it, ladies and gents. Right, and we are now going to move on to the next question. To question 6 we go. They say an object with a mass of 85 kilograms is initially at rest on the ground. It is then pulled vertically upwards at a constant acceleration of 0.75 meters per second squared. Right, so all of those things I would actually highlight. Okay, they said by means of a light inextensible rope as shown in the diagram below. Ignore a resistance, the mass of the rope, or any rotational effects. Okay, so they say draw a labeled free body diagram for the mass while it moves upwards. All right, so we know for sure it's accelerating upwards. So it's suggesting to us, okay, let me just draw it over there. So it is suggesting to us that we are going to have the force upwards. Okay, so I'm going to say that's the applied force. Okay, or you can say the force of the rope. And we have the weight. Or you can say force of gravity. Right, so that's how the free body diagram would look like. As I said to you again, right, the marks do tell me about the number of forces involved. So they say name the non-conservative force acting on the mass. So I want you to note in this case, which one would be the non-conservative force? That would definitely be the force that the rope exerts, right? Okay. So in this case, it would be the force of the rope. Okay, force of the rope. All right. So now they say calculate the work done on the mass by the gravitational force when the mass has reached 11 meters rather the height, a height of 11 meters. Right, so what are we looking for? We're looking for the work done, okay, by gravitational force. So how would we get that work done? So work done by gravity. Note that, by the way, this object is going upwards. Okay, so of course we're going to take upwards, direction as positive. So work done by gravity, that's going to be force of gravity delta x, the cos of theta. Now note, force of gravity, that's mass times gravitational acceleration. So this is going to be 85 rather, times 9.8. The displacement is 11 meters, right? And now remember, we said this angle is the angle between direction of motion. The motion is going upwards, but where is the force? That is the force of gravity, the force in question, right? Or in this case, the force that is being asked, or rather the work done that is being asked, right? So that force is acting in the opposite direction. So the angle between the two is 180 degrees. So that's cos of 180. Okay, so let's calculate that. So that's 85 times 9.8 times 11. Okay, that's the cos of 180. Of course, that makes it negative, right? So that's going to be, so the work done by gravity, that's negative 9163 joules. So that's the amount of work that is done by the gravitational force. Okay, right, now they say to us, state the work energy theorem in words. So remember, we say that the net work done on an object is equal to the change in kinetic energy. Okay, right, I always like writing it down because what you see is essentially what you get in terms of this definition. Right, now they say to us, use the work energy theorem to calculate the speed of the mass when it is at 11 meters. All right, now I want you to note, this time around we are actually looking at a force that is applied, and we've got an acceleration, which means of course it's going to change kinetic energy, isn't it? So let's find out what would be the amount of force that is exerted by the rope. Okay, so if we use Newton's second laws, so I'm going to say, right, so for 6.4, okay, I'm going to say, right, F net is equal to MA. Now note, it would be the force of the rope minus gravitational force, which is equal to MA. So I'm looking for the force on the rope, minus 85 times 9.8. And what does this give me? 85 times the acceleration is 0.75. Okay, so let's find out what the force on that rope is. So I'm going to say 85 times 9.8. Okay, if I take it to the other side, it becomes positive, plus 85 times 0.75. Okay, so that's going to be 896.75 newtons. That's the force that the rope exerts on this body. Right, but we are looking for the work done in this case. So I am, rather not the work done, we are looking for the speed, right, when it's at 11 meters. So I'm going to say, right, so the net work done, okay, so, and in fact, we didn't even need to find the force on the rope. We could have actually done this. We could have just said F net is equal to MA, and what is our F net? our F net, our net force, is 85 times 0.75. Okay, so that would be 85 times 0.75, 0.75. That gives us 63.75. Okay, newtons. That would be our net force. So we can say that the net force is equal to, right? So remember, this is the work energy theorem, right? That net work done, delta X is F net, delta X, the cos of the angle. Right, now what is our net work done? Okay, so we're going to say our net work done, in fact, let me not remove that. So we know that our net work done would be F net 63.75 multiplied by the displacement is 11. Okay, and remember that the net force is in the same direction as the motion of the object. So this would be the cos of 0. So therefore we get an amount of 63.75 times 11. Okay, so I get, so I get 701, right? 0.25. That's joules. But now remember that the net work done on an object will cause a change in kinetic energy. Okay, so we keep that in mind. I'm trying to just look for space here. So I've got this as 701.25. Okay, that would be half times the mass. The mass is 85. Okay, and this is times the change in velocity. So that would be final velocity squared. But remember, we said it is pulled vertically from rest, right? So our initial velocity was 0. Okay, right, so I'm going to just simply divide by half of 85 and take the square root. Okay, so I said this is 7.1, so divided by 0.5 times 85. And please, ladies and gents, I hope that you continue to verify if my answer is correct. So I get 16.5 as my final answer, and now I'm going to take the square root of that. I get 4.06. So my velocity there, apologies that I'm just scrambling for space. So my velocity would be 4.06 meters per second. Okay, right, so please keep in mind, in this case, that's how we are going to get that velocity. Okay, and now we go on to the next question. They say a 30 kilowatt motor is used to lift the mass of 85 kilograms to the height of 11 meters. So now we are not using manual power or energy. We're using a motor, right? They say calculate the percentage in efficiency rather of this motor if it is working at maximum power. Now note, what we can do is to calculate the power that would be exerted by a force, okay, that would lift this guy upwards. Okay, we did calculate that force at some point. So what I'm going to do is, we know that power is, so average power would be equal to the force. So this would be the force of the motor multiplied by the average energy, or I mean the average velocity rather. So in this case, we need to find out what the force of the motor is, right? So what I want us to see there is we remember that we've got the force of the motor minus the, in fact, let's say F net is equal to MA. Okay. Now I want you to please remember, in this case, we've got the force of the motor. Okay, so that would be F net is equal to MA. And we've got the force that would be applied by the motor, right? Remember, we said there were two forces, right? The force applied and the weight. So the force of the motor minus the weight would give us MA, right? So this would be 85 times, actually that's what we're looking for, the force of the motor, minus 85 times 9.8. This is equal to 85 times, you remember that our acceleration was 0.75, right? And I believe we actually calculated this earlier, but we removed it at some point. So we said this is 85 times 9.8, right? If I take this to the other side, it becomes positive, plus this is 85 times 0.75. So I am actually looking for the power, right, due to the applied force of the motor, 896.75, okay, newtons. So this is the force that the motor exerts on this object. Now, so what I'm going to do is, we say average power is the force of the motor. So we got that to be 896.75 multiplied by the average velocity. Now, please note, this object is not moving at a constant speed. So this means that to get the average velocity, we're going to take initial plus final velocity, right? And we're going to divide that by 2. That's how we get the average velocity, right? So our initial velocity plus the final velocity divided by 2. So I'm going to say this is 896.75, okay, multiplied by, our initial velocity was 0. Our final velocity, we found that to be 4.06. And this is divided by 2 because we're looking for the average velocity. Right, so let's find out what the power will be. So that will be multiplied by 4.06 divided by 2. And I get an amount of power there to be 1820.4, yeah, let's say 0.4 watts. Okay, now this is the amount of power that will be exerted by the motor. But now we are looking for the efficiency of the motor, and how we calculate percentage efficiency. Please, I want you to note, right? So we say percentage efficiency. It would be the power that is exerted by the motor, right, divided by the power of that motor. So meaning that in this case, the power that I have here, so that's 1820.4 divided by the total power of the motor, that's 30 kilowatts. So remember, kilo is 1,000. So that's divided by 30,000. And that's multiplied by 100 because we're looking for it in terms of percentage. So we're going to take that value and divide it by 30,000. Okay. and we multiply that by 100. Okay, so I get a value of 6.07%. So that would be the efficiency of this motor. Okay, so that would be the power. So sometimes they call efficiency the power factor, right? So in this case, that is the actually no, that would not be the power factor. Power factor is something else. Okay, so that is how I would get the efficiency of the motor. It would be the power, right, that would be exerted by the motor divided by the power of the motor that is used, and multiply that by 100. And that's how we get to the end of this question. I really hope that you understood it, right, as we move on to question 7. And now we're off to question 7. They say to us, the siren of a rescue vehicle emits waves at 360, at a frequency of 360 hertz. The frequency of the sound is heard by a listener standing along the road is 405. So we notice there that the detected frequency is higher than the emitted waves. So that does tell us that that may be that the rescue vehicle is moving towards, okay, the listener. Now they say to us, define the Doppler effect in words. Okay, so we remember that it is the apparent change in the frequency, the detected frequency, due to the relative motion between the source and the listener. Okay, so please, we need to remember that definition. All right, now they say to us, was the rescue vehicle moving towards or away? So we know it was definitely moving towards. They say explain the answer making use of reference, making specific reference rather to frequency, wave fronts, and wavelength. Okay, so first of all, we know that the frequency, okay, the detected frequency, I should say, okay, the detected frequency is higher is higher. All right, and they said we must use reference to frequency, wave fronts, and so that means that the wave fronts are closer together, right? So the wave fronts are closer together, or closer to each other, I should say. And they said wavelength. So remember that the wavelength is actually shorter. Okay, so therefore the wavelength is shorter. All right, so that is how we're going to explain that. Now, they said to us, take the speed of sound in air to be 340. Right, apologies for that writing there. And they say calculate the speed at which the rescue vehicle was moving. So we know we're going to use the Doppler effect there. Right, so that's V plus minus VL. That's V plus minus Vs times Fs. So notice in this case, we know that our listener rather was stationary. Okay, so that tells us that that's going to be 0. So we've got V divided by V and Vs. And for those of you that have seen me do this section in the easiest way possible, you know that we want a higher frequency, detected frequency, so that this needs to be an improper fraction. So that has to be minus, okay, times Fs. So let's actually substitute the values that we have there, right? So the detected frequency, that's 405, that's 340 divided by, okay, so that's 340 minus Vs, and the frequency of the source was 360. Okay, so, well, it's really up to you how you want to actually just solve this moving forward. Right, so what we can do is we can say this is the product of those two, right, the numerators, okay, and we cross multiply. So we've got 340 times 360, okay, which is equal to 405 into 340 minus Vs. All right, so that makes it easier. If I divide by 405, 405, and I am going to subtract 340. So that cancels with that. So let's find out what Vs would be. Okay, so we've got 340 times 360 divide by 405. Okay, that gives me 302, and I'm going to subtract from there 340. I get negative 37, but remember in this case I would have had minus Vs, is that, so Vs would be equal to 37.78 meters per second. All right, please just verify that and make sure that you get to the same value. Right, so the next questions, next set of questions, they say the driver of the rescue vehicle continues at the speed past the stationary listener. What changes or change, if any, would occur to the following? Okay, they say write down the values of. Right, so firstly, the frequency of the siren as heard by the driver. Now remember, the driver is moving at the same speed as the vehicle, so he will hear exactly the same frequency as the emitted frequency, so that would be 360 hertz, right? Now they say the frequency observed by the listener. Okay, now in this case, what we can do is we can find, let's see, we can actually make a quick calculation there. I think this would really require a bit of a calculation. Or, you know, I think they said what changes, if any, would occur there. So perhaps let's just say less than 360, because then that would otherwise require a calculation. So it would definitely be less than 360, the frequency of the source, right? And then they say the speed of sound in air. Remember, that doesn't change. That would remain the same. Okay, so this would actually have no change. So it would be 340 meters per second. Okay, right, so that is how we're going to explain that. And essentially, ladies and gents, that brings us to the end of this question. 13 marks in the bag, and I know that you would get it absolutely correct. All right, let's go to the next question. And on to question 8, they say we've got point A and B that are 0.04 meters apart, as shown below. They say the sketch is drawn and not to scale. Sphere X lies 0.01 meters from point A, and sphere X has 1,238 electrons removed from the surface. So that already tells you that sphere X must be positively charged. If we remove electrons, then it means that we've got a deficiency of electrons, and that makes sphere X positive, right? So now they say, what is the nature of the charge on sphere X? Choose positive or negative. We've already said that. We know that it's going to be a positive charge. Now they say calculate the magnitude of the charge on sphere X. All right, so now what we're going to do is use our formula. We know that the number of electrons, okay, would be the charge divided by the unit charge of an electron. Actually, let me just use E there. Right, so now we're given the number of electrons that were removed. We know the charge of an electron, and so that means that Q would be N multiplied by E, and so that would be 1238 multiplied by 1.6 times 10 minus 19. Okay, so that's minus 19. And so what that gives us in terms of the charge of the that sphere X, so that's 1238 multiplied by 1.6 exponent negative 19. Okay, so we get a charge of 1.98 times 10 minus 16. Okay, so and that is the charge on the electron of that sphere X. All right, so remember it is positively charged. Okay, so that would be the magnitude of that charge. So that's in coulombs. All right, so they say define the term electric field. We know that electric field at a point is the area where electrostatic force is felt per unit charge. Right, and that is how we define electric field intensity. So they say draw the net electric field pattern for two identical spheres with opposite charges. Okay, so what that would look like, so if we've got two spheres with two charges that are opposite, so this is what our diagram would look like. Okay, so we know that the two charges would exert forces of attraction on each other. Okay, so that is what our diagram would look like. Okay, and please remember, we know that from the positive side, so if we know this is positive, then we know that the field lines would actually be moving away. Okay, or would be moving out, and we know they're moving away from the positive but moving towards the negative, so these ones would have the lines moving in. Right, and please always keep in mind that you are going to actually show, so this is negative. Okay, so if we've got one charge that's bigger than the other, right, then the field density on it should be greater than the one that has a lesser charge. Okay, so meaning more lines should appear there, and please no lines may cross each other. Okay, and make sure that they connect to the center of the sphere. Right, now the next question, they say at what point A or B is the magnitude rather of the electric field due to the charged sphere greater? Explain the answer. Now note that A would be closer to the charge, right? So we know that electric field or the force, right? So they were asking about field. It is inversely proportional to the square of the charge. Okay, so definitely it will be at A. All right, so our answer there should be A. And you can state that the field is inversely proportional to the square of the charge. So the shorter the distance, the greater that that electric field. Right, now they say to us, calculate the electric field of sphere X at point B, right? So at this point here, and they say if sphere X is now is replaced rather with a charge of -2 times 10 minus 9. So sphere X has got this charge, which is -2 times 10 minus 9 coulombs. Okay, and what we want to calculate there, remember they said we must calculate the electric field, right, at point X. Right, so now, rather at point B rather. So we're going to treat B as a positive test charge. So what we're going to do there is we're just simply going to say for 8.6, right, we know that E is equal to KQ over R squared. So the electric field intensity, that would be 9 exponent 9, multiplied by the charge, remember, we said is -2. So remember, we don't need to put the sign for the charge, okay? That tells us the direction of the field, but we don't need to substitute it into the calculation. So divided by R squared, so the distance between X and point B would be 0.04 minus 0.01. So that will be 0.03 squared. Okay, right, so let's calculate that quickly. So we've got 9 exponent 9 multiplied by 2 exponent -9. And we're going to divide that by 0.03. But remember, we square that answer. So that gives us 20,000 newtons per coulomb. Okay, so remember in this case that the direction of that field, since we've got a negative charge over here, all right, so which means that it would attract that positive test charge, so it will be to the left. Okay, right, so that's how we would get the field, the electric field at X, okay, at point B. Right, now the next question, they say a negative point charge Y with a charge of -2.8 nanocoulombs is now replaced at point B. So at point B, okay, right, I'm just going to remove some of that there. Right, so we've got a charge now of -2.8 nanocoulombs, okay, that is placed there. And they say, and a point charge Z, which has a charge of 3.2 nanocoulombs at point A. So we've got positive 3.2 nanocoulombs. Okay, right, now they say to us, draw a vector diagram to show the direction of the forces on charge X, right, because of charges Y and Z. So remember, in this case, when we look at charge X, it is negatively charged. So which means B, charge B, would exert a force of repulsion, actually. So because they are both negative, so which means that B would repel charge X. Okay, so this would be the force of B on charge X, and A would actually attract that. Okay, so this is the force because of A, so this is the force, and I said E there instead of F. So this is force between B and X, this is the force between A and X. Okay, so I'm expecting the force between A and X to be much bigger because of that distance. All right, so they said we should draw that vector diagram, so we did that, showing the two forces. So this is the force of A on X. This is the force of B on X. Okay, right, so that's how our vector diagram would look like. Okay, showing us that they are going in the same direction. Now they say to us, calculate the net electrostatic force on X because of the charges Y and Z. So let's look for the force of A and X. So we're going to say this is KQA, QX divided by the distance between them, R squared. That's 9 exponent 9. The charge on A, we said that's 3.2 nanocoulombs. Please remember, nano is times 10 minus 9 multiplied by the charge on X, which is 2 nano. All right, so that's divided by the distance between A and X. Note that the distance between them is 0.01. Okay, so that gives us squared there. All right, so let's calculate quickly. In fact, we could have made that much easier for ourselves. We already had the field. So that's 3.2 minus 9 times 2 exponent negative 9. And this is divided by 0.01. Apologies there. That's squared. So I get a force of 5.76 times 10 negative 4 newtons, right? And remember, that force would be to the left. Okay, so this would be to the left. So now I need to find out what is the force of B on X. Again, we're going to do the very same thing. So I'm just going to substitute the values there. So this would be 9 exponent 9. The charge of point B, that's 2.8. And please note that you do not need to substitute the signs. Okay, and we know that X is 2 nanocoulombs. And the distance between B and X, we said this was 0.03. Okay, another way to find that force, because you already had the charge, the field rather, is that you could have multiplied the field. You can use the equation E is equal to F over Q, right? So you want the force, you already have the field, so you could have just multiplied by the charge on sphere, the charge on X. Right, so in this case, we get another value. Okay, let's try and calculate that quickly. I'm just going to change a few values at the top. Okay, so that's 2.8. And remember the distance between B and X is 0.03. Right, so again, let's find that in scientific form. That's going to be 5.6 times 10 negative 5. Okay, and remember that's newtons. They are in the same direction, so also to the left. Okay, we did specify that they are going to, sphere X would be repelled by B and it would be attracted by A, right? So in this case, what we're going to do is to find the net electrostatic field. So we are going to simply say it's going to be the force of A on X. I said A on B here. A on X plus the force of B on X. So we can actually add the two up. All right, so I've got that value there, plus the 5.76 exponent -4. Right, and what do we get for a final answer? Okay, so let's get that in scientific form. Okay, so right, so we're getting all sorts of weird values there. 1.2 times 10 -3, is that correct though? Okay, yeah, I can see that I did something wrong there. So that's 5.76 exponent -4 plus I've added 5.6 exponent -5. Okay, let's get that value. Yeah, so that looks like the correct one. 6.32 exponent -4 newtons. And so please remember, it will be, even though they said, okay, so we actually need to specify the direction. Okay, so that is going to be to the left, or you can say east, rather to the west, in that case, if you wanted to use the points of a compass, right? Right, so in this case, that is how we're going to calculate the net electrostatic force. I hope that you understood that as we go to the next question. Now let's go on to question 9. They say we've got a circuit diagram that is set up as in the diagram below. They say resistors R1, R2, and R3 are identical. Switches S1 and S2 are closed. They say ignore internal resistance. Right, so now they say use the diagram above to answer the following questions. Firstly, they say state Ohm's law in words. I hope that you know that law off by heart. It says the current across a conductor is directly proportional to the potential difference provided temperature remains constant. Of course, I've seen other versions that say potential difference is directly proportional to the current provided temperature remains constant. All right, so that's how we are going to mention that. So they say name the component of a non-ohmic conductor in this diagram. Now, remember that when we talk about a non-ohmic conductor, rather, it is a conductor that obeys Ohm's law, right? So remember that if you look at any of these conductors where we would have a non-ohmic conductor, a light bulb, because remember, the brighter it burns, it tends to generate heat, and as a result, it will actually deviate from Ohm's law. So we would say component L. Okay, so that would be component L, which is our light bulb. Now they say on the next one, write down the reading on the voltmeter with both switches closed. All right, so if we note there, so the voltmeter would actually be reading the parallel voltage. All right, so which means it's the same as the EMF. So which means here our voltmeter would have a reading of 12 volts. Okay, and switch, now they say switch S1. Oh no, actually I filled in the wrong answer. So that would be with both switches closed. Now they say switch S2 is open. Now the moment we open switch S2, what it means is that those two resistors actually are not connected to the circuit. There's no current flowing through them. They say write down the reading on the voltmeter. Okay, so once again, even with switch S2 open, the reading on the voltmeter there would still be that 12 volts again. So that would still be 12 volts. And the next one says switch S2 is closed. So which means we would have current there, but they said S1 is opened. Now note, when switch S1 is open, it means there's no current that's flowing into our circuit. Okay, no current is flowing. So now they say write down the reading on the voltmeter V. So that would be 0 volts. Okay, since it won't be connected to the other side of the battery. Okay, so we'd have 0 volts there. So they say switch S2 is opened. How would this affect the emitter reading? Okay, right, only increase, decrease, or stays the same. Now, the moment we open switch S2, okay, then that means that we are actually removing resistor R1 and that light bulb over there, right? So what this does is that it will increase the resistance. Now remember, once you remove resistors in parallel, it means that we're going to actually increase the external resistance of the circuit, right? And now that means that once resistance increases, we will therefore decrease the current. Okay, so in this case, they said S2 open. How will this affect the emitter reading? So that will definitely decrease the emitter reading. The current would decrease, right? Okay, and then finally, they say both switches are closed. R1 is removed. How would this affect the voltmeter reading? Okay, so we close both switches. We remove resistor R1. All right, so in this case, by removing that resistor, we are actually going to have the external resistance of the circuit is actually going to decrease, right? So we've removed that resistor. So they say, how would this affect the voltmeter reading? Actually, that does not affect the voltmeter reading at all, since in this case, remember, it would still give us the same 12 volts. So we say it will stay the same. All right, so that is how we reach the conclusion of this question paper. Ladies and gents, we've come to the end. And of course, if you are still struggling with physical science, please look at the description of this video. You will get all the information you need for our center and all our extra classes. Just get in touch with us. And of course, our camp is coming. Please do make sure that you are a part of that. And I promise you will sort out all of your issues in terms of maths and science. Otherwise, ladies and gents, it's been a pleasure being with you. And please don't forget to subscribe and like. And please do share with your friends. I'll see you guys next time. It's Shop Shop.